morning. Thanks for joining me today. We had a lot of great questions that came in, and so I'm going to try to address all of them. So we're going to talk about the open channel flow measurement today. So what is considered an open channel? Open channel is defined as a flow in any channel in which liquid flows with a free surface. It can be a rectangular channel, round pipes, streams, sometimes occasionally full pipes, and through primary devices such as weirs and flumes. So what are some of the challenges in calculating flow in an open channel? We're going to discuss how you can calculate the flow rate, the application, does it have enough up and downstream room to get at uniform flow, and what technology should we use? So what is needed to measure open channel flow? You need a primary device, which could be a weir, that could be a flume, and then you need a secondary device, which would be a flow meter or a flow logger. But first, let's talk a little bit about a weir. So what is a weir? It's a dam built across an open channel in which liquid flows over it. So we are concerned about the water going over the top of the weir. A weir provides a flow rate that is proportional to level, and you may have seen a different variety of shapes for weirs, which could be a rectangular, a V-notch, trapezoidal. These are all different weir shapes. But let's take a closer look at the weir. So as far as the sensor placement is one of the bigger questions I get on where I should read the level. And where you measure the level from is we have the head measurement point, which is 2 to 3 times the maximum head height of water going over the top of the weir. And that's going to be determined by what your expected flow rate is through that channel. And why that's important is that if you have the sensor too close to the weir wall, there's a drawdown effect. As you can see with this drawing, it draws down and the level could be a little bit lower, closer to the weir wall, which would then give you a calculated lower flow rate. So how high should the weir wall be? It should be 2 to 3 times the minimum head height, which will be determined by the expected flow through that channel. And a couple of things, we want to make sure that the weir wall is high enough that we get a free flow over the top of the weir, which creates some ventilation on the opposite side of the weir. Now, as far as when measuring flow or head height with a weir, we are concerned about the water going over the top of the weir. So that where it says the maximum head height, that's the water that we're concerned with going over. So when you do a level measurement, you determine what the weir height is, you would measure the overall depth and then subtract the height of the weir wall. And then that would give us the level of the flow that's going to go over the top of the weir. As far as the straight run in front of a weir, it should be 20 times the maximum head height that you expect to see over that weir. And as far as the more straight run of pipe you have upstream or channel, the better, because what we're looking for is a uniform flow going through or across this weir. So as far as next, we want to talk about the calibration of partial flumes. But first, let's just discuss what makes up a flume. So a flume provides a flow rate proportional to flow, similar to a weir. It restricts the flow to accelerate the water going through the throat of the flume, which makes it a little, somewhat self-cleaning because the accelerated velocity going through that flume. That doesn't mean that it's maintenance-free, but it does reduce the amount of maintenance needed when you use a weir over a flume. But there are 3 parts to a flume. You have the converging section, is where the water comes into the flume. The throat section, that's where the water is accelerated through the flume, and then the diverging section where the water exits the flume. Let's take a closer look at that. So I have people call and ask, what size flume I have, and to determine that, you measure the width of the throat, and that will determine the size of your partial flume. Where you take your level measurement at is H sub A, which is going to be 2/3 the length of that weir wall. You can reference the ISCO Flow Data Handbook. They'll show you where that point is, or contact your manufacturer. When you order the flume, a lot of times they'll put a ruler or staff gauge at that location, or make a mount for your sensor to make it easy to identify where to take your level measurement from. So here's a look at a Parshell flume with an ultrasonic sensor. The primary devices are weirs and flumes. The same level sensor can be used with both, with a weir or a flume. So with a flume, the flow calculations are based on level. So we take the level, we apply it to a formula depending on what size or type of flume you have, and that will give us a flow rate. So flumes are good for free flow applications because they have the assumption that the water is always going one direction, free flowing through the channel. It is unable to detect reverse flow. So in a little bit, we'll talk about other options if you do have reverse flow. And if you have reverse flow through a flume, you do have bigger problems to worry about. So in this example here, having an improperly sized flume or debris going through a flume can cause problems. So as the picture shows, we've got water backed up through that flume. Water is still coming out the other side. So some maintenance is required with this. And what you'll notice is that your water level is going to go up, your flow rates are going to be higher than expected, and so this flume is backed up due to debris. So what would you expect through this? You're still going to get a flow rate reading, but it's going to be much higher than the actual flow going through there. But what are your options on this? Well, one, set up a regular maintenance schedule to clean the flume out, or two, have an alarm set that if it ever gets to a maximum flow rate, somebody needs to go out and inspect it. Or the other option is to put an area velocity sensor upstream, because an area velocity sensor will read the level and the velocity. In this case, it would read a high level but almost zero velocity to give us an accurate flow rate. So some tips for calibrating. One, you can use a staff gauge, or when you order your flume, they'll put a ruler or sticker on the side of the flume that has the level measurements. You could calibrate your level to 0 with no flow. This would be your most accurate way to do it, although it's usually not practical to stop flow going through a flume. You can use a stilling wheel. Stilling wheels are a great way to measure the flow because you don't have the velocity of the water going through that could ride up on the ruler. And so you have the stilling wheel on the side. It makes a nice, easy place to get an accurate level measurement. And you could also use a calibration target. So with ultrasonic sensors, we have a calibration target that you put in the flume. You set it to a known height. In this case, the example showing 3 feet. And so you'd have your target mounted in your flume. The ultrasonic sensor would read the distance and what the level would be at the target, and then you would calibrate your flow meter to, in this example, 3 feet. So it's a nice, easy way to do it, and you don't have to worry about the velocity going through, and you have a fixed depth that you're calibrating to. Another good idea is to use the ISCO Flow Data Handbook or the manufacturer's lookup table. And so with that, you would look at the height or depth, water depth, and then find out the associated flow rate, and your flow meter should match that. Other types of flumes are the Palmer bolus flume. So this is a little bit different. The water goes through the flume. We're concerned about the water going over the top of the flume. But what makes this different is that it has that upper transition. And so we have the arrow pointing to the 0 point. So at the top of that upper transition is the 0 flow. So that's where we want to calibrate the level from the 0 point up to the water surface. So when doing this, you would measure the overall depth where the red arrow is at, and then subtract the upper transition. So you want to pay attention to the offset, and the way you can figure that out, that offset, the formula is the diameter of the Palmer bolus flume divided by 6. So in this example, we have a 6-inch Palmer bolus flume divided by 6. The upper transition is 1 inch. Now you should reference your manufacturer's flow data table. ISCO has a flow data table, but if you're using other vendors, their flow calculations may be slightly different just due to the way they built the flume. Another question that came in about Palmer bolus flumes is the maintenance. They had noticed that they were always getting sediment on the upstream side by that upper transition. So that's kind of the give and take of a Palmer bolus flume. The advantage is that a lot of times you can insert them into an existing pipe, but because of that riser, that upward transition, you can and will get sediment build up in front of it. So you do need to have a maintenance schedule to go out there and clean that periodically. A couple tips I've seen when I've been out in the field with the technicians when they're taking level measurements is they will use chalk or powder, put that on their ruler or stick, put that in the water, and then it's going to wash off, where the water is, and then you just measure up to where the remaining chalk is. One I recently saw that I liked is they used washable markers. So they had a metal ruler or stick that they put in there, and they used the washable marker, put it on there, and the same thing. The water washed off the marker. You just measured up to where your ink was at, and that was your level. Nice, easy way to do it that's less messy than using chalk. Another option, especially if you have high velocity, is to measure from the top of the pipe. So in this example, what we do is I would measure the ID of the pipe. In this case, it's 12 inches. We'd have 6 inches of airspace. So I'd take 12 minus 6, and then that gives me 6 inches of water depth. So I would then calibrate my level to 6 inches. This comes in really handy if you have high velocity, because if you put a ruler in an application that has like 5 foot per second velocity going through there, it's going to rise up on your ruler, and it's going to be difficult to get an accurate level reading because it's going to rise up on the ruler anywhere from 1/4 inch to 1 or 2 inches, and it's then at that point it's just kind of guesswork as to what the actual level is. So this approach may be more accurate for you. So calculating flow with the primary device, it requires a level to flow equation. There are common level sensors that are used with the weirs and flumes. You can use an ultrasonic sensor, which is non-contact, mounted above your flow stream, so you don't have to worry about debris getting caught in the sensor. There are radar level sensors that also mount above your flow stream. Or you can use a pressure transducer. Pressure transducer is mounted on the bottom of your channel. When you order a flume, you just tell your vendor what type of technology you plan on using, and they will usually can usually accommodate you to set up the appropriate level technology to work with it. And you can also use a bubbler. So a bubbler, the way that operates, measures the amount of pressure it takes to push out one bubble at the end of that bubble line, which would be equivalent to the water depth. So what are some of the challenges with flow monitoring? Debris in the channel, maintenance, and installing sensors in high flow. So what I mean by like difficult application, it's that it could be a channel that occasionally surcharges. It might not be practical to install a flume because it's just a difficult location, or it's too expensive to install a flume. So some of your options are to install a non-contact area velocity flow meter, such as the laser flow, or you could offset an in-pipe area velocity sensor to the side of the channel, which I'll show you. But first, the laser flow sensor, the way that operates, it's going to mount above your flow stream. It uses an ultrasonic sensor to read the distance to the surface of the water. When we know the distance, now the laser will focus below the surface of the water. The laser's on for about 2 seconds and takes 5,000 spectral readings to get our velocity. The other option was to offset the sensor in the pipe. So if you have an in-pipe area velocity sensor, traditionally you're going to put it at the 6 o'clock position on the bottom of the pipe. But if you have issues with sediment or debris collecting on that sensor, well, then it becomes a lot of maintenance. So what you can do, take the sensor, offset it to the side of the pipe, and then you would calibrate your level. So in this picture, if that was 6 inches of water depth and the sensor was at the bottom of the pipe, I would calibrate my level to 6 inches. If I rotate it up to the side of the pipe, now I'm 2 inches off the bottom, I would still calibrate my level to 6 inches because that's the actual water depth. And this is just an example where they had 2 sensors in a channel. They were getting sediment on there, rotated off to the side, and we're getting great data after that. Other questions I get are how much straight run of pipe or channel do I need for installing an area velocity sensor? Well, the biggest thing is you need uniform flow, because we're taking a velocity reading, and without uniform flow, it's going to be difficult to get accurate flow readings. So the rule of thumb is that depending on who you ask, we'd like to see at least 5 diameters upstream, 10 upstream and 5 down. Other people you ask are going to say 5 up, 2 down. Really, it's specific to the application. You have to look at the application and determine what is upstream. Do we have pumps or bends? How fast is the velocity? Because with the faster velocity, we need more straight runs. We have something like a bend or a pump upstream. It's going to create more turbulence. And the idea is we want to make sure we have uniform flow before it goes across or underneath your area velocity sensor. All right, another question that came in is how do I put together a complete scope that includes all the required cables and connectors? For example, they have a ISCO 2150EX with the 2194EX. So with that, I would, you could go to the ISCO website and download the 2150EX manual, and they have this example in there just showing all the parts and cables, how it goes together. The main thing is the 2150EX is in the hazardous area. We have a network cable that goes over to the essentially the network isolator, which is our 2194EX barrier. And with that, then we can power it with AC to DC power pack, solar panels, batteries. So as long as we're in the safe area, then we can use all the traditional options for powering the equipment. Another question was, I'd like to build a guide for flow characteristics to determine which technology should I use. There's a lot of things to take into consideration for that. Some of the things I start to ask first is it safe to install that equipment in the pipe? Do you need to read reverse flow? Is this an application that's tidally influenced that maybe have reverse flow in there? Is sediment or debris an issue? So before deploying equipment, I like to ask them to go out, look at the site, look at the ladder rungs, other things around there for signs of surcharging. And then how long is the study? So, if you're only going to be out there for, 10 minutes doing a spot check, then we're not so worried about the sediment or surcharging because you're out there on site. So the answers to these are going to determine, what technology do I use? If I'm going to use an in-pipe area velocity sensor, or if I need to use a non-contact one because there's surcharging. The duration of the study will determine if I need AC power, solar panels, or batteries when I go out there, or possibly even using a modem. If it's a location that's difficult to get to, you may want to consider using a modem. That way you can monitor the site remotely. If it's a short study, like you're only going to be out there spot checking, we have a metering insert, which is a small weir with an inner tube around it, slides in the pipe, restricts the flow, and then it uses the level over the weir to calculate the flow. It's a great option for short studies and spot checking. Another question was, can you go over or provide information about case studies using AV sensors, monitors, develop a rating curve for, what they want to do is they want to develop a rating curve by using an area velocity sensor. I do not have a case study on that, but I have worked with people over the years on this, and what they've done is they've taken an area velocity sensor, put it in the channel, let it run for, a day or a week to get a nice flow curve. And so what I've done with the ISCO flow length software, now I've taken the level and the flow rate, and as you can see in this example, the level and flow changed quite a bit over this 3-day study. And then I was able to export the level and flow rate to develop a flow table. So I just exported all that, I sorted it, and then now I have the option to pick however many level to flow rate data points that I want to use. So continuing on that, how can you use the level only to calculate flow? One, you can just use a level to flow rate table. So the ISCO flow data handbook has lots of tables in there depending on what your application is. Or you can use a flow calculation to determine your flow rate. Other options are using the Manning formula. So if you have a round pipe, elliptical, rectangular channel, you need to know the slope of the pipe, which will calculate, it's part of the velocity calculation, and you need to know the roughness. So with the slope and the roughness, then you can use the level to calibrate your flow. Now this is making the assumption that you have a free flow application. The difficult part is trying to figure out what your roughness is. In these examples, we have a concrete channel, but there's still some vegetation in there, so it makes it a little more difficult to figure out what your roughness coefficient is. Another question was, could you tell us something about Doppler sensor calibration? So first, when using an area velocity sensor, the formula is area times velocity to get our flow. So what do we need? We need we need to know what the pipe geometry is. So we need to know that it's a round pipe or rectangular or elliptical. We need to measure the water depth. So when we know the water depth, we can calculate what the wetted cross-sectional area is in that pipe. And next, we need the average velocity. So when we have the average velocity and then the wetted area, we can now calculate the flow rate. So with the area velocity sensors like the ISCO in-pipe AV sensors, we use Doppler to read the velocity. And so we output a 500 kilohertz signal and read the frequency shift. And so what is a Doppler effect, as we're shown here with this ambulance, is that it transmits a sound, in our case 500 kilohertz signal, and then it reads the frequency shift back to the sensor. So as the sound or particles are moving towards the sensor, you're going to get a higher frequency, and as it moves away, it reads a lower frequency. Another example of that is we have our AV sensor in the pipe with the pressure transducer to read the depth of the water. It fires a 500 kilohertz signal, bounces off all the particles, air bubbles in the water to give us an average velocity from that frequency shift. But the question was, how do we calibrate velocity on an AV sensor? The velocity calibration is not required because it is just it's the theory behind the frequency shift. We can calculate the accurate velocity on it based off the frequency shift. So it doesn't really matter if I'm outputting a 1 megahertz signal or a 500 kilohertz signal. It's reading the Doppler effect or the frequency shift to come up with the velocity. But if you insist on calibrating because it doesn't match another flow meter, historical data, it doesn't match. It's one of my favorites when they say for 5 years I've been getting the exact same flow rate and it doesn't match that. I find that hard to believe sometimes, but or if they just say the flow rate doesn't look right, or it doesn't match my influent flow. There are some options. So with the ISCO signature 350 area velocity sensor and the laser flow sensor in the advanced programming, we have a velocity coefficient. It's going to be labeled under coefficient B. And so if you have an offset that you want to put in there, that is where we can enter that offset. Or afterwards in the FlowLink software, we can apply a coefficient to it to adjust the velocity and recalculate your flow rate. Another question was, can I use an AV sensor in a full pipe for flow rate calculations? Yes, it worked well for that. So at that point, the flow rate is proportional to velocity in a full pipe, similar to a mag meter. So before, we used the level to calculate area, but now it's full, we get 100% area. The advantage of an AV sensor is it can read reverse flow, as well as mag meters can read forward and reverse flow in a full pipe. So the AV sensor is ideal for surcharge applications, tidally influenced pipes that are, for the most part, non-full, but then they would occasionally go full when you get reverse flow. Some AV sensors, area velocity sensors, have temperature sensors built in. What's nice about that, and I recommend that you log the temperature, because if you're doing an I&I study and your flow rates change and you see that the temperature starts to drop, that's an indication that you're getting rainfall in your pipe, because you're going to see the temperature drop as your flow rates are changing due to rainfall coming in. Another option for calibrating AV sensors, like the ISCO sensors, they are temperature calibrated, and so the advantage of that is you can take that sensor, calibrate it to 0 level in open air, and then install it in your channel. I've found, especially on higher velocity applications, this ends up being more accurate than trying to put a ruler in the water and measuring, because how the water rises up on the ruler, it makes it difficult to get an accurate level reading. And as far as our sensors being temperature calibrated, the idea behind this is to avoid drift due to compensation. So sensors that don't have it would require you to take the sensor, put it in the water for 5 to 10 minutes to let it acclimate to the water temperature, and then calibrate your level. If you didn't do this, then you put it in, you would actually see a level shift due to the temperature. More questions on the AV sensors. Somebody is when it's in troubleshooting, help on how to read negative flows, and if there's any creative ways to test your sensor. So what our technicians have come up with is they've used an aquarium air stone, and they put it in the bottom of a tube. So as you're seeing here, we got like a 4-inch or 6-inch PVC tube. They put an aquarium air stone in the bottom of it, and then the AV sensor will read the speed of the bubbles coming up to the surface. They rise at a rate of about a foot per second. Kind of depends how close you are to the air stone. But for reading reverse flow, just turn the sensor upside down so it's facing the ceiling, and you should be able to read the air bubbles going away from it. So this is a pretty inexpensive way to test your area velocity sensors without having to build a big flow loop. Other ways to measure reverse flow or determine the quality of your area velocity sensors, like with the 2150 and the 350 AV sensors. We have diagnostics built in for signal strength, measures the amount of reflected energy received. It's an indication of the gain applied to the signal. A lot of times you're going to see this in around the 60% range. The spectrum strength is the return signal from the signal that's been sent out. It's an indication of the true velocity versus the noise. And then last, the spectrum ratio, it tells us the direction of the flow. So example of that spectrum ratio, in this case, you would see all the water is going one direction, you should get 100% ratio indicating all the water is going one direction. But if you see something like this where the water is swirling, then you're going to have a lower ratio, which could be down to 0 if it's seeing equal positive and negative velocity. This is helpful when you have an application that is starting to get dropouts on velocity, where it was working fine and then now we get a poor ratio and possibly negative velocities. Well, if there's debris in front of the sensor, it could create that swirling, and that could be an indication you need to send somebody out there to clean that channel. So you can be proactive with this, and you see the ratios start to drop and your spectrum start lowering, send a technician out to clean it before it gets completely covered. Other questions that came in are about the laser flow sensor. I want to discuss the initial and flow on calibration to maintain accuracy. What's required for routine basis, how often. I want to discuss the Doppler power. The minimum suggested Doppler power is 1,000, and discuss the accuracy. So as far as when you install a laser flow sensor, the only calibration required for that is the depth calibration. If it's difficult to get into the pipe, we can use the distance. So the laser flow sensor will automatically tell you what the distance from the bottom of the laser is to the water surface. But what I recommend is when you install the laser, take a physical measurement of the bottom of the laser to the bottom of the channel. And then now when we have the distance reading from the sensor itself, we just subtract the distance from the overall distance to the bottom of the channel. What's left over is going to be your level. Now, as far as the calibration frequency, it's really site-specific, and a lot of it is driven by local regulations on how often you have to do that, or just your standard operating procedures. Now, with that said, if just talking to people all over the country, a lot of times they'll go out 2 to 4 times a year to do level calibrations. So they go out and just check the application, calibrate, or verify that the level is still reading properly. The other question was discuss the minimum Dopplers to assure accuracy. By default, it's the equipment's set to 1,000 for minimum Doppler. And so what that does is it provides an adequate signal-to-noise ratio to make sure we're getting a good return signal. So as you can see with that graph on the bottom right, the Doppler power is calculated off the entire area underneath that curve. So you see that curve A, that is built by the 5,000 spectral readings that are taken when the laser's on for 2 seconds. And so the Doppler power reading that you're going to see is going to be dependent on the turbidity of the water. So the dirtier the water, the higher the Doppler signal you're going to see. The cleaner the water, the Doppler power is going to decrease. It doesn't mean that it's a better or worse reading. It just means that we have more or less particles in the water. And then the distance away from the water is going to have an effect on that Doppler power reading. But what we're looking for is we just want the Doppler power to be higher than the noise level. So in this example on that bottom right, C, that's just the electronic noise level. We just want to make sure that we have a higher signal than the noise, so we get accurate flow readings or velocity readings. Another question came in was discuss the accuracy of flow rates under the minimum 0.5 foot per second. So as far as our testing and verifications, all been done down to 5 foot per second. I do not have accuracy specs below that. However, we have had lots of applications that have read velocities slower than that, down all the way down to 0.15 foot per second. As far as those readings, they look accurate. The customers I've dealt with have also thought that was an accurate reading. You'd have to do some independent testing with bucket and stopwatch or something. If you have that slow velocity, you probably could do that. All right, now that it's colder out, I've had several questions coming in about cold weather, and this person is having problems with they're getting like ghosting with their ultrasonic sensor when it's cold out. They were asking about cleaning the face of it. So yes, cleaning the water droplets off the face of the sensor could help. So if it's mounted in a vertical orientation with colder weather, sometimes we get steam coming up. You get water droplets developing on the face of the ultrasonic transducer. The water droplets can freeze, and then that could cause some problems. So one thing you can do is we sell a horizontal mounting bracket. And so if you mount it horizontal, now those water droplets should go to the bottom of it and stay away from the face of the transducer. So that could help minimize that problem. All right, for the portable samplers, the question is the 750 module a better solution than strictly ultrasonic when they have flow conditions 50 to 250 gallons per hour? It kind of depends on the application. You know, if you already have a flume in place, or if the debris is an issue, you know, flumes are, you know, highly accurate, been used for a long time, so you know the ultrasonic may be a better option. But you know, but if you have a flume application and it's been known to surcharge, you know, using level only would not be ideal, because the flume is assuming or expects the flow to go one direction, so it would not be able to read reverse flow. So in that case, an area velocity sensor like the 750 would be better. One thing you'd have to take into consideration, so I know we have the flow rate, but I don't know what size channel that is. But we need at least 1 inch of water to cover the sensor to be able to get a velocity reading. With a 750 sensor, the velocity should be greater than ½ foot per second. And another thing to just watch out for is that if you do have really slow velocity, you know, below 2 foot per second, you're going to start getting sediment and stuff dropping out of the flow stream, which could eventually cover the sensor. So other options for that, especially if you have the slow velocity, is use a laser flow sensor. It's going to be non-contact. We don't have to worry about debris collecting on it. Other options is, depending on the channel, put a polymer bolus insert in, and then you can continue to use your ultrasonic sensor. Or consider using a 730 bubbler. So I need a little more information on this application to better answer that, but the nice thing about the bubbler, if you did have issues with steam or foam, the bubbler would not be affected by those. So how do you control interference of steam or ice buildup on meters exposed to elements? Our facility has a few flow meters that echoes under these conditions. If you have the ultrasonic sensor, you could try setting the blanking distance on it. The default range is 0 to 10 feet. You can set that a little bit closer, so if it's getting stray echoes, it could filter or ignore the outside echoes. I've had people vent the manhole to, you know, instead of a solid manhole cover, have it with the grooves or vents in it to allow the steam to escape. Other options would be to go with a bubbler level system, because the bubbler would not be affected by wind or steam or foam on top of the surface. And another possibility is using a radar level sensor, because the radar sensor would be able to penetrate the steam and foam. A similar question is they'd like to monitor the level outdoors in a weir box in freezing fine weather in Minnesota. What's a good non-contact solution for detecting ice level or water level in the weir box? So yeah, our options are kind of limited here. I know you mentioned you wanted to use a non-contact, but a bubbler may be a good option for that. We have like a 4-foot stainless steel bubble tube that you could put down the side of that channel. It's, you know, the surface of it is you know, small, so it's not likely to collect rags or other thing on it. Or you just have to take manual readings. You know, have a staff gauge installed on the side of the wall, and somebody would have to go out there and take a look at it. You know, other non-contact options would be the ultrasonic level sensor or possibly a radar level sensor. Next question is, customer that's currently using the laser flow area velocity flow meter under normal flow conditions. They get 6 to 15 MGD. Under heavy flow conditions, they are developing foam on top of the water, which could create problems, because the ultrasonic or the laser flow sensor uses the ultrasonic sensor for level, and if it cannot penetrate the foam, it's going to go into error. So an option for that is that you could install use the bubbler again, or use a radar level sensor, and then with the signature flow meter, we could have it switch over to the other technology. So what we could do is develop a flow rating curve, level to flow curve off of the laser flow sensor, and then we could switch over to using the level of the bubbler or radar sensor when you do have the heavy foaming conditions. One of the questions that came in was about the laser flow sensor located several hundred feet upstream from a weir. Assume the flow rate is still calculated area velocity. So yeah, it does depend. Yeah, if it's several hundred feet upstream, it probably isn't affected, by the weir. So as far as the velocity is going to be slowed down a little bit, but at that point, you're still getting a free flow through there. So the area velocity formula should still work on that. If it was closer to the weir, where we essentially had dead space, dead water because of that weir wall, then we would have to take into account for that. And what I've done in applications where the laser happened to be closer is we were able to program in a silt level to essentially remove that wetted area where the water isn't flowing. All right, another question is, how does the laser flow meter account for varying flow velocities in a pipe when calculating flow? What areas in the pipe does the laser cover and how deep? Well, as far as the varying flow rates, the laser flow is reading the just below the surface of the water, because what we're looking for is the peak velocity, which is below the surface. So as your water depth changes, the flow rates change. The peak velocity still remains just below the surface where we're reading the velocity to then calculate an average velocity. And as far as the other part of that question is how deep does the laser penetrate below the surface of the water? We have the option to set it to read at 5%, 8%, and 11% below the surface of the water. So as the water depth changes, it looks at the depth and then does calculation at 5, 8, and 11%, with a maximum focus depth of 6 inches below the surface of the water. Another question was, what is the maximum distance from the water for the laser meter to measure accurately? We can mount the laser flow sensor up to 10 feet away from the water to be able to read the level and velocity. Another question was, what's the possibility of adding an AV sensor to the laser flow and have an average or switching option? And what does the AV sensor use for depth? So yeah, we can add an area velocity sensor. We can either put it on the bottom of the laser flow sensor, we use that as, we call it our surcharge sensor, or we have the ability to put a AV sensor in the channel. And with the signature meter, we could use both velocities and average them to calculate a flow if you wanted to, or we can set a trigger in there so that it when you get to a certain water depth or flow rate, we can automatically have it switch from the AV sensor or to the laser flow sensor. So we do have a lot of flexibility with our programming to be able to do that. And the other part of that question is on the AV sensor, what is it used for depth? It has a differential pressure transducer that has a range of 0 up to 10 feet. Another question came in with regards to the base of the channel when using a laser flow meter. The client has a lot of debris that's difficult to remove from the bottom of the channel. That's difficult to measure because you do not have uniform flow going through that channel. So when any area velocity meter, it reads that velocity and it expects to have uniform flow going through there. In this case, it does not. So with that application, you would get trending, during your storm events and normal flow. But it would be difficult to get a real accurate flow reading through there. So they would have to go in and clear that debris out. Some other technologies like our older 80 FM acoustic Doppler flow meters that automatically profile the flow stream might work better in that application because they would be able to read the different velocities throughout the channel. But at the end of the day, my recommendation would be to get something in there, clean it out to get accurate flows. Another question was somebody was looking for a calibration certificate on the AV sensor. Contact ISCO customer service, get the serial number off that area velocity sensor, and we can get the calibration certificate for that. Let's see, would it be possible for the laser flow to see the pressure differential and use it as opposed to the sonar? No. As far as the laser flow sensor, just by design, it's using the ultrasonic distance. That's the key thing. It's using the distance from the bottom of the laser to the top of the water to determine where it needs to focus. Then the second part of that question is, yeah, they have foaming. So yeah, that would be one where we may want to use two different technologies and just switch between them if foam is an issue, or try to resolve the foaming, by getting some type of sprayer or something, upstream to knock down the foam.